Hey, my name is Jordan Deshawn, and this video is about Step 3 in the new Pumped Safe Water Design tool. Step 3 is about hydraulic design. And here in Step 3A, we're going to define the design flow rate. If you remember, this icon here indicates to you that it might be helpful to use an optional calculator for this step. And we can click this blue hyperlink to take us directly to the Optional Calculators tab. It highlights the table of interest, and you might remember too, highlighting or hovering over any of these cells with a red triangle in the top right corner makes these notes appear that give helpful explanation to the optional calculators and terms used. But we enter the design water demand and then the estimated hours of operation per day for the system to get the estimated design flow rate of 5.6 meters cubed per hour. So we can see the design engineer has written that value here. And then the question's asked, is the design flow rate less than the allowable yield? And we see here NA, or not applicable. The reason for this is that, if you remember, in step 2, we learned that the yield test has not been conducted yet. So we don't know with certainty what the allowable yield is. So it's not quite applicable yet. However, the allowable yield was estimated based on water sources in the area. So that was 120 cubic meters per hour, which is much, much higher than 5.6. So this would seem to be acceptable, but we would confirm after a yield test is conducted on the new borehole. So there's an explanation box where you can answer the question how the design flow rate was chosen. And then step 3B is about the system layout. And we're first going to answer what kind of pump is being used. So this is a good time to remind you that this tool is not applicable for gravity systems. This is intended mostly for pumped water systems. So the two types of pumps you could choose are submersible or surface. And depending on which one you choose, you'll see a helpful diagram here that shows you how water will flow through the system, from the borehole, through the pump, through the water treatment, and into the water storage tank. You'll also notice that this diagram shows the elevation of these relative to each other. So you can enter those here, and they'll populate as well in the diagram here. Next, in step 3C, we're going to look at total dynamic head, which is calculated as the sum of static head, friction loss, minor loss, and treatment loss. First, static head is automatically calculated based on this equation: the elevation at top of tank minus the elevation at the dynamic water level. From there, you'll enter the piping system components, the length of pipe, the inner diameter, and do note this is the inner diameter of the pipe from wall to wall, not necessarily the nominal diameter. Then the roughness coefficient, which we can see here in general, we recommend 135 for plastic pipe and 120 for metal or GI pipe. And then a column for the minor loss coefficients. And here at the beginning, we can list out the pipe sections and describe here the section of pipe that's being described here in the rows that follow, or columns that follow. So for the first one, we have the pump to the wellhead, the riser pipe, and so on for the rest of the supply system. Now for the minor loss coefficient, you might be wondering to yourself, how do I calculate these? There's not much of an explanation given. Here you can use the optional calculator to sum the minor loss coefficients. This takes you to the optional calculators tab, where you could enter in the blue cells here the quantity of fittings for a particular section of pipe length. So for example, if you had 2 elbows, maybe 1 T, and 1 gate valve for a particular section, you would then see here on the bottom right the sum of the minor loss coefficients based on what you've input here. So if you repeat this for each pipe section, you can simply copy this value for each pipe section and enter it here in the table for the minor loss coefficients for the particular pipe section you're working on. After that is the treatment losses, and first we can enter the number of treatment units in parallel. We had 2 erosion chlorinators we're using, and that automatically calculates the head loss through the erosion chlorinators at your design flow rate. If you used treatment equipment that was not a water mission treatment equipment, you could enter that value here of the other treatment loss, and you might have to get that from the manufacturer or specifications about the treatment equipment you're using. Also, you can use the optional calculators tab to estimate the number of treatment units in parallel. So how did I know to use 2 erosion chlorinators? Let's click on that optional calculators to see how. We first entered the design flow rate, which is 5.6 meters cubed per hour, and then it automatically recommends to us the number of units of the LWTS or the erosion chlorinator needed. You can do the same based on the maximum flow rate of the other treatment if you're using a different type of water treatment equipment that's not common to water mission. Continuing on, this then gives us the total treatment loss, and all of that combines together. The static head, the friction loss, the minor loss, and the treatment loss sum up to give us a total of 75.3 meters of total dynamic head. And that takes us to the summary of step 3, where we get the 2 main outputs from this step, the design flow rate and total dynamic head. So that's the end of step 3. Next is step 4, which will go into pumping. Thanks for tuning in, and as always, if you have any questions, please feel free to reach out to a Charleston engineer. We are always happy to help.